very much for the invitation to this very interesting workshop. So I'm Tadashi Takayanagi. I'm working on string theory. And the string theory side of this quantum entanglement, but recently there are some big interest about tensor network, and especially tensor network called MERA, which is a conjecture to be connected to a gauge gravity correspondence or a so-called ADS CFT correspondence. And I would like to introduce this subject in this occasion. And so these are the contents of my talk, and I mainly focus on the continuous version of tensor network, so-called CMERA, continuous MERA, which is initiated this work 2011. Kayagema was born, and Belastrate. And so we have several ideas to how to relate this CMERA to holography, and I'd like to explain these ideas. But this is, mainly for this audience. We have in mind this condensed matter audience, so I'd like to first explain from the elementary level about what is a holography or ADS CFT correspondence, which is one of the most important topics in string theory subject, and also connection to so-called MERA, multi-scale entanglement renormalization, which is currently becoming hot topic as a part of self-introduction of myself. And after that, I would like to go to the main part of this lecture, which is about continuous MERA. So I would like to explain how to construct the CMERA, continuous MERA. And maybe describe some application to excited state. And today's lecture will be probably finished here. And in my Monday symposium talk, I'd like to give more details about the connection between CMERA, continuous MERA, and the gauge gravity correspondence. So today's talk is first we start with the motivation, which is related to holography, and I should say it's quite ambiguous, and then go to the construction of continuous MERA. And my symposium talk, I will explain some more detailed connection between them. So let me start with what is the holography. So of course, I need much more time to explain more details about holography or ADS correspondence. But my argument is very short. But if you are interested, please just ask me later. So, but one basic starting point is so-called black holes. The reason why we consider black hole because black hole is kind of simplest but highly non-trivial laboratory for people who are working on quantum gravity, including string theory. So black hole is a good laboratory. And it's highly non-trivial, but quite simple in a theoretical distribution. But anyway, so we are thinking about following process. So how to make black hole? So we have a lot of materials. Sometimes dust or stars, small stars, or any matter. So lots of matter. Let's assume we have a lot of matter, and we just compress it in a very tiny, small region, like kilometer size of solar mass object. Then what we find is a so-called gravitational flux. And then what we find is that this matter is actually makes a black hole, so-called black hole. And black hole, the meaning of black hole is like this. So we have some observer outside, and this is a very, very heavy object. But if this observer wants to see inside the black hole, but this observer cannot reach inside the black hole because of the very strong gravitational force, and even light rays is a massless particle, and even light rays cannot come out of that because of strong gravitational forces. And the border beyond which this observer cannot see inside is called horizon. And this is a very important geometrical characterization of black hole. So black hole is surrounded by so-called horizon. So this is a quite surprising phenomenon which only happens for gravitational theory. Of course, this is only happens in gravitational theory. And that in other words, there are interactions so-called Newton constant. This is non-zero. So Newton constant in gravitational force. And so once we form this black hole, so the information which is already So information of this matter, like how many spins and spins up or down, or some number of some particles, they are actually hidden inside the horizon. Only quite limited number of observable are available, like only charge and mass. It's quite few, only a few, compared with the detailed information. So people think there are some hidden information inside. It's included in the black hole, but in physics we want to quantify. We already have some quantitative description, and so we want to measure the amount of hidden information, and this is people usually use entropy. So this leads to the idea of black hole entropy. Then, so we can look at general relativity to estimate the amount of black hole entropy. So this can be done in classical gravity. So, and in the end, we reach the idea of so-called very famous Beck-Einstein-Hawking entropy. A black hole entropy. So this is a quite a universal formula. So we can apply this formula to any background, like flat space or space-time with a cosmological constant and so on. So this formula is very simple. So just we account that, so just we estimate the entropy included in this region, black hole. So this is, and we keep all, only here we keep all constant, physical constant like Boltzmann constant and light velocity. But later I just fix this to just, we call it just one. And Newton constant and h bar times area of black hole horizon. So this is a quite universal formula, and if we assume Einstein general relativity, this formula is always true. So there are no counterexamples, not so far. And this formula is very interesting because, first of all, it includes all of the famous, very important fundamental constant in theoretical physics. This is Boltzmann constant. This means we need to understand some statistical mechanics. And this is relativity, it's a velocity, right? And this is, of course, gravity. And h bar, we should understand, of course, quantum mechanics. So we need to combine quantum mechanics and gravity and so on to understand this formula. And another surprising aspect is this part, this area. So this area, we take this horizon. So let's think about four-dimensional, three-dimensional space-time and one-dimensional time. So space direction is 3D, like our universe. And we have some black hole, just some kind of sphere. And horizon looks like two-dimensional sphere. So horizon is two-dimensional, so it's like area. Volume is three-dimensional. So usually entropy is proportional to the volume. But here, in this formula, in the context of black hole entropy, it's always proportional to area. So this means it's not extensive. So at first, this looks very puzzling. But anyway, this is, just honest result which come from general relativity. In general relativity, we can find some analog of thermodynamics and we can estimate entropy.
Question?
Yes.
So is this formula valid for any dimension? Or
Any dimension, yes.
So Gn has different dimension.
Yeah. This is true. Any dimension. Yeah.
So in 2+1D, this area has a dimension of length.
Into three dimension. 2+1. This becomes just length.
Yeah. Gn.
It's just one dimension. It's a one dimensional. Yeah.
Are there corrections to this formula?
That's a good question. Yeah. So here we assume it's so-called Einstein gravity. So action is like this, by the Newton. This is Einstein Hilbert action. So we assume this. And we can add some cosmological constant or any matter field, if you like. You can add any matter Lagrangian. But the correction appears if we talk about higher derivatives, like R squared or any higher power. Then we have some modification of this formula. So this comes from, in string theory context, this is some related to stringy correction because string theory has a length, minimum length. That's the reason we have some UV finite theory. It's like alpha prime, for example. This alpha prime is string length square. So R has a length and it's opposite length minus 2, so it cancels out. This is one possibility. Also, another possibility, we can also add some higher order, about the Newton constant, some power of Newton constant. And again, we can have some higher power. So this is related to quantum gravity. Quantum gravity correction. There are two possible corrections to this formula actually. So, yeah. So, but we are talking about the limit where everything goes to classical and it's simple, that is Einstein gravity. And when curvature is very small, then we can forget about this stuff. So I'm only talking about that case. But in general, we have some correction to that's correction to that. And yeah, so this is non-extensive, but it usually have a volume. But this looks confusing, but people like Tofu and Sastan, they think this is actually fundamental principle in gravity. So because in gravity we don't know much about what is the quantum mechanics of gravity. So just we should be just honest. And we just don't know. So let's take this principle of gravity. So this is the idea of holography. This is So the idea is here just a very kind of a primitive idea. So we are talking about degree of freedom in gravity, but we can look carefully so that we think about some quantum gravity. So this is actually described by service area. So just you can just imagine this idea just from here. And more concretely, so we can talk about some gravity is defined in some space-time, which we usually call bulk. So gravity is here. Gravity is here. And this gravity is nice theory, but actually, equivalently, if we count the degree of freedom, this degree of freedom is actually also counted by boundary of this space-time. So gravity in bulk. Gravity in bulk is equivalent to some quantum system, quantum minimal system, some quantum system, which lives on the boundary. So this dimension is lower by one dimension. So this is consistent with this one. So gravity side, it looks area, but from this quantum system viewpoint, it looks like volume. So I agree with what we call extensive entropy. And so this is a idea of holography. And maybe in condensed matter setup, maybe you can think of some topological initiator or quantum Hall effect. We have some bulk and boundary. So if we put some bulk, so if we put some NO at the boundary, so it's like related to some bulk non-trivial deformation. But here, everything is dynamical. Gravity, bulk also dynamical, and the boundary also dynamical. So this is of course this is quite a vague idea, and at that time it's just conjecture. But after that, we find some concrete example, so-called ADS CFT correspondence. So that's the next thing. Also let me also emphasize this quantum. I'm saying this is quantum system, but there are no gravity. Of course, there is no gravity here. We call it a non-gravitational theory. Okay, so now, so at this point it's quite a vague idea, but later. 1997, Margasena formed a very nice realization of this idea in the context of string theory. But just forget about string theory, just write down some idea of ISSP. So ISSP means, so we have some, so pictorially we have something like this. So we have some space-time called ADS. ADS is the anti-de Sitter space-time. which has a negative cosmological constant and has a maximum symmetry. So that kind of space is unique. It's called an ADS space. And so it's in particular metric we can write this way. So we have some radial coordinate called z, and the z square x mu. So mu runs from 0 to d. So my convention is that we call it ADS d plus 2. So we have a d plus 1 dimension here, and d is z is one more dimension. So this x mu is just a Lorentzian space-time, so we have a Lorentzian space-time here. It's a foliating along this called extra dimension called z. So each slice, if we fix z, we just have a Minkowski space-time like R1. So ADS CFT claims that gravity in ADS, and also we can think about quantum correction, so we can think about string theory. So that it includes quantum gravity effect. But this gravity in ADS d plus 2 is equivalent to so-called conformal field theory on R d plus 1. Conformal field theory is a kind of relativistic quantum critical point. So it's a quantum critical point with maybe, dynamical exponent equal to 1. It's relativistic conformal field theory. And d plus 1 dimension. So that means space dimension is a d. So this is a d-dimensional quantum critical point. Just one is a time direction. So this is a claim. And the reason why this is related to this holography is that we have this anti-De Sitter space, but at z equals 0, so z equals 0, actually we need some cutoff, so we put it to very small quantity efficient. So this is a boundary of ADS. D plus 2. So we have some boundary here. And where we suppose that this conformal field theory critical point theory gives here. So this is an idea of ADS CFT correspondence. And the first check is that we should have some same symmetry. And just geometrically, this space-time we can show that this has some nice symmetry. 2 d plus 1, SO d 2 comma d plus 1. This is the Lorentz signature d group. And conformal field theory also have the same symmetry, 2 d plus 1. So this includes SO 1 comma d, which is just Lorentz symmetry of this d plus 1 dimensional space-time, but it has a scale invariance and so-called special conformal invariance, so it's symmetry there. And there are so many tests against this proposal. This originally derived in some very heuristic idea, which is related to so-called D-branes in string theory. But of course, we need to check a lot of things. The correlation functions and energy or entropy, they match very nicely. So people now, string theory community people believe this is true. And but precisely, we should say this CFT is something called holographic CFT. This is a holography, so holographic CFT. And holographic CFT is two properties, which is large N. Not all of the CFT have this property, so that's the point of this. So large N and strongly coupled. And so large N means degree of freedom is quite large. If we talk about gauge theories, it's like SUN gauge theory with large N limit. And the interaction is very, very strong. And if we lose these two constraints, if we forget about these constraints, then we have a lot of quantum correction here. So we can still expect something like this, but it's so different from Einstein gravity. To find the classical Einstein gravity, we need these two conditions. So that's we can learn from this first example in ADS CFT correspondence. And so one more important point is, so anyway, we find some one extra dimension here. So what's the meaning of this Z? So I will come back to this again, but we can easily understand because this scaling of Z is related to scaling of X. So we can Z goes to lambda Z, and X mu goes to lambda X mu, and then metric is invariant under this theory. So that means this Z direction, scale of Z direction is correspond to the scale of the field theory, the scale of these quantum systems. So Z is related to the length scale of the theory. So in other words, so what ISSP is doing, roughly speaking, is a kind of Fourier transformation. So we have conformal, we have some D plus one dimensional system. We have some system, but we decompose degree of freedom into each Fourier basis, like high energy mode, low energy mode. And high energy mode, information of high energy mode is stored, information is stored near the boundary, when Z is very small. So this is quite UV information. And if we talk about long wavelength data, then it is actually stored in a large Z part. So it's like kind of length scale slice we are taking, and we store information at each point. So that is roughly speaking what this correspondence is doing. And this is manifest, I think, in the description of tensor networks. And so let me comment. This is a compact version. There are some compact version. This is just another version of this. So this is called global ADS. And these are quite technical points, so maybe you don't need so much care. But sometimes I use also in this talk, my talking on Monday. Just looks different, but it's essentially the same. So this anti-Tadashi space satisfies the Einstein equation, which is negative cosmological constant. But this has another solution, but it's just equivalent to this solution by coordinate transformation. So in that sense, it's a gauge equivalent. But sometimes it is quite useful to use this solution. So this is a D-dimensional sphere metric. And this is a radial direction and space direction, sorry, time direction. So it's like it looks like a cylinder. This time direction here, and the rho direction is here. Rho is a radial direction. And this rho is something similar to this Z. But now boundary structure is a little bit different. So boundary, so this global ADS, the boundary is given by, so we take a rho goes to infinity. So this is a boundary. So it looks like R, time direction, time density. So it's a compactified situation. And in a, for example, 2D case, we have some flat plane, and also cylinder, cylindrical coordinate. We just kind of coordinate transformation in conformal fusing. So this sometimes this is quite useful. I'm going to use it. And yeah, maybe let me mention that. So, two generalization. Of ADSFT. There are many generalizations of ADSFT, but roughly speaking, always they are divided into two classes. So first one is a gap case. So we can add some, so this is a kind of gapless theory, quantum critical gapless theory, but we can add some relevant perturbation. And if we go to the infrared, we have some gapped theory. So this is a gapped case. So if we talk about high energy region, even though we add some relevant perturbation, still theory doesn't change. Relevant perturbation is not so important at the UV. So UV geometry, so we have some Z direction, and so this is Z equals 0 is a really UV region. And if we go to larger Z, we have infrared. So UV geometry is same as ADS, this metric, but it's modified in the infrared and actually disappeared. So there are some critical states that we can call it Z0, and this is a roughly correlation length scale in the gap-2 system. And below which there are no space-time appear because degree of freedom, we don't have any degree of freedom here. So this is a gap-2 case, and this part is almost same ADS. So it's a correlation. Another thing is that finite temperature. Finite temperature case. So this case, we have some z direction. And so again, z direction, but now we have a temperature scale. So in other words, it's inverse, let's take an inverse temperature, theta. So this should play a very important role here. It's an inverse temperature scale. And again, even though we have some finite temperature, if we go to the infinite high energy limit, we don't care about temperature. So high energy limit is again same as ADS. This part is same as ADS. But something happens at the energy level at beta. So this is an inverse temperature scale, beta. And here, actually, what we find is the horizon of black hole. So we actually have black hole. So as already mentioned, black hole has an entropy, and this is just equivalent to thermodynamic entropy, thermal entropy of this finite temperature system. So this is of course this is proportional to volume, and this is again proportional to area in a vacation cooking. So that way they are consistent with each other. But always UV geometry is the same. And such a condition is called asymptotically ADS, and because we don't do anything about UV limit of the theory, we only modify infrared part of the theory. So, and most of the generalization of ADS is always cast into these two defined possibilities. Okay. So these are my simple and very brief introduction of the ADS CFT. And now I'd like to explain about the quantum entanglement. So we can compute many things by using ADS CFT correspondence, like correlation function and also this entropy. Entropy is actually here it's an area of this black hole horizon, and that reproduces thermodynamic entropy and so on. So, and the generalization of such entropy is entanglement entropy. So let me explain holographic entanglement entropy. So this entanglement entropy is also a useful quantity to characterize tensor networks. So just let me mention that. This is based on my work with Shinsei. Well, there are many developments of this. But just I'm giving a simple, these are simple calculation. So we have some, again, have this kind of ADS safety correspondence. So let's take just time slice, t equals 0. Simply just focus on static spacetime, no time dependence, just some particular time slice. And as usual, to define entanglement, we divide space, this is just space, into A and B. And then we are talking about A and B, so we are talking about reduced density matrix, no way. And compute entropy. And that's in an ADS CFT, it's a very simple description. So it's like we have some subsystem A and B, and just decompose any way you like. And so we have this decomposition at the CFT side, which lives on the boundary. On the ADS side, gravity side, we have one dimension higher always. So we extend this boundary of A and B, which is the most important thing to define this, in the bulk. So here it's bulk. And we call such a surface gamma A. Gamma A is, of course, end on. If we take a boundary of gamma A, end on the boundary of A. This is just definition of gamma A. And then this entanglement entropy CFT is now mapped to some geometrical quantity in anti-De Sitter space, and it's just given by minimum area. So this area of gamma A divided by coordinate and gamma A satisfies this condition. So this is the formula already we have seen. This formula exactly same as Bekenstein-Hawking formula of black hole entropy. But this formula is actually more general in that this gamma A is no longer a black hole horizon. We don't need any black hole in this space-time. It's a and also we need to take a minimum area. So this is minimum area. The reason why we need to take minimum area is roughly equivalent to solve Einstein equation. This is actually equivalent to Einstein equation. So you can think of some variation around that. We somehow, this entropy is kind of partition function on some topological manifold. And we want to evaluate partition function, and we apply some variational principle. And we always need to optimize result. And this optimization is corresponds to this minimization. And there are some similar structures in tensor networks as well come back. And also, this already also shows that. So if we take this size of A with L, so let's take the size of linear length is A with L, then the property of ADS space-time tells us the size of this gamma A in a z coordinate is absolute. So this means that, so this is exactly the probing scale. We want to probe the scale, where wavelength is roughly L, L inverse. And if we want to probe the length scale L, then we need the geometry. We need the information of the geometry which is up to z equal L. So this is the length scale. So if we are just interested in UV information, like very tiny region, and talk about the entanglement between tiny region and outside, then we only need the information here, up to here. But if we want to find the information which is very larger scale, then we need to, this minimal subset go extend into the bulk areas and deeply, and we need some more detailed information of the infrared method. So like this. So if we talk about just the entropy for this small system, we don't care about this part, correlation X. But if we talk about larger scale, it's really care about this correlation X. Okay, so these are my introduction to the ADS CFT and its some entanglement properties. So now switch to the tensor network interpretation. If you have any question, please. No? Okay, then let me go to the interpretation in terms of MERA. By the way, so for example, one comment is that we have some metric, ADS metric with singular at z equal 0, like this. I will have some at z equal 0, and metric that gets divergent. And this divergence is equivalent to the UV divergence of quantum field theory, degree of freedom of infinity. And from the viewpoint of entanglement entropy, so this divergence precisely gives area law divergence, which is common to local field theory. So area law of entanglement entropy just comes from the contribution. And infrared contribution gives finite contribution. So let me now talk about ADS and connection between ADS CFT and MERA. So we put question mark because this is some problems still, and we need some refinement of this idea, which is also my main topic of this my talk in Monday next week. And so, but anyway, this is a quite attractive idea, and that's the reason why string theory people got very interested in this technique of tensor network. And the first person who pointed out this is Brian Swingle, 2009. And he conjectured that ADS CFTs might be equivalent to the MERA network. This is kind of conjecture. At least we can say these are both of the ideas both are based on renormalization group, maybe I should say real space renormalization. And at first sight, it looks indeed similar. And but if we look more carefully, we can find the following similarities. So already, I think the talk by explanation by Glenn about this talk and also maybe more. There are many discussions already. So let's take a 1D MERA. This means supposed to describe 2D CFT, one time dimension and one space. And so this is my sloppy way of writing. So I first apologize that. So and we have many spins to cause grain. So this means a kind of isometry. This is isometry. And we cause grain. So two spin gets into one spin. Two spin gets to one spin. And then we end up with just one spin. But this is not enough to explain the highly entangled system, ground state of this critical point. So we need to add something called disentanglement. So this is a unitary transformation between two spin to two spin. And of course we need to put more. So this is just 8 spins. But the fact that this notice is that so this is just a simpler system. We can generalize more, looks more nicely. But let's take this subsystem A, some subsystem taken here, and evaluate this entanglement entropy. Of course, it's quite hard to precisely compute it even if we just have this diagram. But this diagram is very nice that it describes some wave function, structured wave function in graphical way. But anyway, we take this region A, then what we can roughly do is we can give some upper bound. So these two regions is connected to the other part through these networks, through these bonds. So we can talk about zero freedom of this bond is chi, as people usually do in community. So then maximum entropy, which is carried by one bond, is log chi. So this we can have a bound of this entanglement entropy log chi. This is the 1 unit times number of intersections. Number of this intersection. So let's call also this gamma A is very similar there. It's just any curve which you can make right, which end on this boundary way. So you can also choose other gamma A like this. This is also fine. But always we have this bound, this gamma A, and this Tensor MERA network. So we are counting number of bonds. So this is always works. And though we are not sure this is saturated or not. But very naive guess is if we have some generic system which is really quite entangled, maybe we can have a following scaling. And of course we should optimize this bound so that it gives a minimum value. So we change gamma A and minimum. Maybe only after minimization, there might be possibility that this is saturated. So we're not sure. But if this is true, then this is very similar to this formula, this entanglement entropy. So the holographic entanglement, I just said HE. So this is a big motivation for single conjecture this connection. And if that is true, so what we find is like this. So this whole geometry which MERA makes is identified with time slice, because here also we take the time slice, ADS, and ADS3 because we are talking about 1D, 2-dimensional cell. So this is, in other words, mathematically this is something called hyperbolic plane, 2-dimensional hyperbolic plane, H2. So this is a rough.
Excuse me, are you going to specify what kind of MERA we are talking about?
Because yeah.
MERA can represent many things. On the other hand, ADS space is just one kind of thing.
Yeah.
So
Here I have in mind the MERA for if strongly coupled, we can say the strongly coupled gauge theory, and which are the UV find. UV find that means some conformal invariance, and then we construct MERA. Then that's correspond to this. That is a precise way of saying. Yes. But at this point, everything is vague.
Right.
Yeah. That's exactly true. And in the end, we want to see some. We need to find some conformal field theory, which is holographic, and that is actually strongly coupled and larger gauge.
Question.
Yes.
But this does not rely on being strongly coupled or large end or anything, right?
Yeah, you're right. Yeah. So actually, I mentioned that, and that's a big issue. And actually, it looks nice. It looks nice, but if you look closely, there are many problems about these identities, and that is exactly related to these questions. So, but this is quite heuristic argument. And the problem, which I want to mention the problems. This area is MERA. And there are many things, but some of them is somehow, I think now it's almost resolved, but some of them is not. So let me list it. First one is a symmetrical issue. So we want to find some 2D CFT, and this has a very nice symmetry, which is conformal symmetry, and that's also completely realizing anti-Doshita space. But this is actually missing here, especially symmetry so-called special conformal symmetry. It's not clear how special conformal transformation is. Of course, the ground state which realizes the boundary, this has of course all symmetry, but this network does not seem to respect that. That's one big problem. Of course, this is a scaling variant. Scaling variant, but other symmetry is not. This is one problem. And related, I think this is closely related, is that there are some causal structure. And so if we look closely at this network, if we modify this state, then that evolves along some light cone. There's some light cone. But we don't expect any light cone because this is a spatial manifold. This is not no time here. So this contradicts actually with each other. So there are some causal structure in MERA. But we don't have any. Not in H2. But actually there are people suggest that this might be, I think this first placed by Benny, who is quantum information service, and the 2011 or something. And maybe rather than 82, but MERA might be much closer to Doshita space, two-dimensional Doshita space. Doshita space is so Doshita space has a time. It's like look if we write coordinate system, it's cosine hyperbolic square, dt square, and rho square. So expanding the universe, it's like sorry, it's t. T square, cos t square, hyperbolic, exponential increasing of space time, maybe like this. So this is, but issue is that both have the same symmetry. Both have the same symmetry algebra, H2, but this is a timeline. It has a different light cone, and this light cone structure seems to be very similar to this. And I will explain how to understand this issue in actually on Monday, so probably not today. But anyway, so this is one causal structure problem, but they are probably closely related. And of course, another thing is why this is a very naive argument. Why this is saturated? This is entanglement. Entanglement entropy bound saturated. This is the question. And actually, these three are in a discrete tensor network, these three is actually now almost resolved by so-called perfect using perfect tensor. Tensor network, which is Presky, Yoshida, Haruo, and the people worked out. And that's also mentioned in my paper. And so yeah, this is a question. But these three might not so difficult to understand, but the final one is very difficult to understand. Still, I should say, still not resolved. And this is related to strongly coupled and larger issue, which Kawashima-san mentioned. And so this is actually related to bulk locality. Sub-area scale. So this is a very technical word for the string cell connectivity, but what does this mean? So we are talking about the Einstein gravity. So we have some nice spacetime, classical spacetime, anti-de Sitter space, and which has of course curvature R. R is a ADS radius, so we have like this. So this is appear here. But we expect Einstein gravity can be applied so that length scale is larger, much larger than Planck length scale, but still we can take this length scale to be much smaller than curvature scale. So of course Planck length is the shortest distance in gravity, so quantum gravity, so we cannot go further. But as long as we keep length scale is much larger than Planck length, we should understand the physics better. And we don't need to care about this R, which is very large scale, which is related to curvature of this space-time. So if we cannot probe curvature scale, then there is no reason to think about this generality. So this is what what is meant by this locality. So we want some locality which is much larger than Planck scale, but much shorter than ADS scale. But however, if we use this MERA diagram and just literally translate into ADS3, so each bone has actually, roughly speaking, this structure has a order R, ADS scale. So it's like we want to find some Planck length scale discretization of this hyperbolic plane, but what we find is a very large discretization like this. So this is a problem here. And this should be related to large n and strong coupled. Gauge theory. So this is definitely, we need some more development.
So,
yes.
Do you mean that the intuition here is that the MERA is sort of capturing some sort of mean field? What is really going on?
Mean field.
Or some effective description of.
Yeah, roughly speaking, this tensors, if this kind of correspondence is true, then roughly this tensors gives the information metric.
Okay.
In that sense, we are giving some mean field approximation to Einstein gravity.
Yeah, but it's not giving you the fine grain structure.
So sorry.
It's not giving you what happens. I mean, you said it, no? Below the ADS.
Yeah, that's a problem. Anyway, so in that sense, we cannot say precise mean field because even Einstein gravity, we expect that we can probe this distance shorter, even in mean field approximation. So that's a problem actually. So this is a big issue. I think people are trying to understand. But these three is actually nowadays have some better understanding, and I will also give some continuous version of that understanding. Okay, so these are introduction to this kind of heuristic idea how this ADS space-time related to MERA. So, any further question? If not, I'm going to continuous. So now I just forget about all of these. Just focus on continuous MERA. Just review and also introduce some modest progress about continuous MERA. Anyway, these are fine because this MERA network is true for free theory and Ising model and everything. So of course it's quite natural that we cannot find this part locally, but we need more sophisticated network to understand this. And but if we take continuum limits, I mean everything can be smoothed out, and there are some hope that continuous limits can solve these problems, and that's the motivation why I'm working on continuous MERA. And so we started the MERA diagram, which we wrote. So it's very correct, but we add some dummy state. So, yeah, so it's coarse graining, but it's Hilbert space dimension is decreasing, but we add some dummy state so that we just artificially keep all same Hilbert space dimension. Dummy states. And take continuum limit. But this is, we have to be very careful. It's not that clear how this is connected to this one. But anyway, this is the idea. And once we formulate it, we can just work with this formulation. So we have some, so this is anyway radial direction. So we have some length scale. This is a length scale. We have some length scale direction. And so we write it just following the literature. So let's write this U. So, and U equals 0, we have some UV theory at this point, like this point. And U goes to infinity, minus infinity, and we have invariant. So everything becomes trivial. So we have some network here. And if we take particular value U, so we have some state which we call psi U. Psi U. And so usually, I mean, in Wilsonian renormalization group flow, effective action changes under the length scale, energy scale, but here state changes under the length scale. So this is the idea of this entanglement renormalization, MERA. And its continuous version should have the property. And so this U is something, some coordinates which introduced, but so match with the literature. So but this is related to the length scale, which is Z, which is in the ADS coordinate, but roughly with this mark. Epsilon is a UV lattice spacing, UV cutoff. So if we want to rewrite this in terms of ADS, we have this kind of. And anyway, so this formulation, so we have this psi U. And this is defined in continuous way. Because we add some dummy states, we can just write everything in terms formally in terms of unitary transformation. So U, and it's a continuous integral. So these steps becomes continuous. And ds, as plus L, and like this, and the IR state. So omega IR is a state here. Omega IR is the IR state, and that means the same as this 0, 0, 0, 0, 0. This means that 0, 0. Trivial state, but this is actually quite non-trivial from the viewpoint of quantum field theory, and in a continuum limit. And so these are the non-real, so I will come back to this later. So no real space entanglement, but this is actually described as something boundary state in quantum field theory. And yeah, so there are two operations, and L is a coarse graining. This is a scale transformation. Space-like, scale transformation. So this means that we don't care about time direction, just only space direction like this, we just coarse grain. So this is not something we usually consider in relativistic field theory, but only appears here because we only think about time slice and we coarse grain in space-like way. But this is quite important. And because everything is 0, 0, 0, 0, so this should be also invariant. IR space should be invariant as space-like scale transformation. And that means we are going to fix point. And this KS is some K-dependent operation. my importance of it. This Ks is actually giving entanglement or removing. So this is this entanglement. Or adding entanglement from look this way, but we can also reduce entanglement from this side. So this Ks is written formally in local expressions. So it's like some, let's take x and some operator, local operator, but with some cutoff always. There are some regularization, so we can define UV cutoff to be 1 over epsilon cutoff, and it's some cutoff operation. With some, and also so we can have some functional dependence of S. It's KIS dependent. So, but it's local, it looks like just integral of every contribution. So this is basic formulation of this people worked out. And of course, this is the two format, and I will give some explicit example, which are some free scalar theory. Just
In this formulation is omega IR of
Yeah,
entanglement, so Ks is actually entangler.
Yes, yes, yes. Yeah, yes, exactly. So, yeah, the people quote this, so that is exactly. And let's focus on 2D CFT, 1D critical point. So there are some nice properties which we can summarize, which is so related to this work and this previous work. This is my previous work and also something currently we are working. So in 2D CFT, so we have nice properties of Virasoro symmetry. This is the format of this. Between any space. So there are nice infinite dimensional symmetry, and we can use this to characterize the theory. So first of all, so we want to understand this omega IR, no entanglement, but actually there are simple construction. There are some simple way to construct this, and we can just identify this as a boundary state. So the boundary state, the reason why we choose boundary state. So boundary state is just a defined boundary. So we have some path integral, but we cut it at the boundary, conformally invariant boundary. And if we talk about correlation function like this, 0 or 1 or n, so this is equivalent to this picture. So we can have some regularization. Boundary state is singular, so there is some very small regularization. So delta h. Here, this length is 2 delta, and we insert operator, n operator here, or 1 or 2 and n. And this is factorized into one point function because this boundary is so close. We have some MERA of each operator, and we have factorized into n copy or n products of one point function. So that means there are no non-trivial correlation between these 2 points. Any 2 points. So in other words, this is quite disentangled case. And in a specific model, we can also explicitly compute entanglement entropy for boundary state, and we actually confirm that in this paper we confirm that for free Feynman, we can confirm real is 0. But of course, boundary state has some level related to primary, and entanglement entropy can change actually depending on the level. But if we correct one, at least in a specific model, we can have a 0 entanglement. And if we choose different level, then we have some finite non-vanishing entanglement. But still that's very small because usually in 2D CFT, so we have entanglement entropy for this logarithmic formula, this famous formula, and some constant. And this logarithmic divergence is always gone if we take any boundary state. So, and only constant parts can change, but if we choose proper one, at least in some specific model, we can show this. And this means that we can choose particular combination. This is we have two copies of Virasol algebra because we have in 2D we have left moving and right moving. So we particularly choose this linear combination. Then the definition of boundary state is like this. So this satisfies this. This is one point. But of course we need to put some regularization. One way to regularize this boundary state by this one, but there are some choice. We can choose other regularization. So there are some AUT. And the second point is that, so if we add these two, and the Ks and L, this is a disentangler and post-graining, and this actually gives some L prime, which is a relativistic fixed scale transformation. And in a field theory language, it's like quantum system is like this. EXT, this kind of operation, this energy stress tensor. But anyways, this is something we are very familiar with in conformal field theory. So we define this total sum. And also L itself has just a geometrical meaning. We just change the radius. So we define some state on some compact file radius, and we just squeeze its length by just changing metric. And then what happens about this field, like phi or phi dot phi, and we just talk about it, and it's actually given by sort of Bokoli-Bok transformation, and that defines this N. So in that way, and we can also define this Ks. So this is a very formal description. And third one, actually there's a very nice property. At least we can see this property in a model which we explained. Next is a free scalar model. So it's nice property is that actually this Ks, this disentangler, actually commute with this Ln, some linear combination of Virasol algebra, and also this L after some proper interpretation. So this is consistent with the choice. So we argue that IR state is a boundary state and satisfy this constraint, but consistent with, and we need to scale invariance of the IR state, and these two are consistent because this is already satisfied, this is already satisfied. We require to be satisfied, so and if we just commute them, it's always should be there. So some kind of consistency condition. But this is the important property, and this is a conformal invariance. So similar. So this is something we don't find in MERA, discretized MERA, but in a C-MERA, there are some also special conformal invariant is respected in this way. So this is one of the program, only one, but one of the four programs which I mentioned.
So maybe I'm a bit confused. So in standard MERA, the degree of freedom decreases as you approach to the top of the.
Yes.
But if I understood correctly, to formulate MERA, you actually kind of introduced the branch. So in usual MERA, two sides it's shrinking to one side. So there is some tree structure, but you introduced some branch to 0.
Yes. Here.
Without the number of degree of freedom or something. Then you start from IR repeats. So
Yes.
number of qubits is the same. So
Yes. Double qubit we keep it the same.
You apply some
Yes, unitary
operator to describe this evolution.
Yes.
IR limits. But then, so most of qubits in the IR limits are kind of dummy.
Yes.
Yeah.
Yeah.
And so I don't see how it matches with this continuous description, because in continuous description you just have state of some CFT.
Yes.
Not exactly CFT, but giving
Some
it the same Hilbert space as 2D CFT. So can we see those
yeah,
ancilla qubits?
Because we are, but roughly speaking, so anyway, we start with ground state, and we in the end we end up with IR state, and they are interpreted. And this is a boundary state, which is rarely, for example, Neumann boundary state, as you know, it's like written by this quite, local condition, and it's like this says that we can have we have some many points. Many points here, but all points mean that just up spin. So because of this local constraint.
So somehow those ancilla qubits are already embedded.
Yes, already included. But I agree. So precise connection is not clear. Nobody I think works out it. Yeah, that's I think very interesting.
Somehow the claim is that you start from this simple boundary state in IR.
Yes.
Right, this exponential
yes.
operator, then
exactly.
you get desired.
Yes.
State.
So yes, exactly. So in that, hopefully, boson it's like we have something like this coherent state that's very familiar, and this kind of boundary state, and this lambda start with 1 because here it's like boundary state, but lambda goes to 0 here, so that it becomes vacuum. That's something we are doing. Yeah, so now I just come to this free boson example. So this example similar for free scalar. Free massless scalar. Massless scalar. So, but this is of course everything is solvable because massive. Because of Gaussian. So just initially. Maybe I should use the fermion, but for high energy theories, the scalar field is much easier. So that's like vacuum scalar field. So maybe not so realistic, but but this is a Hamiltonian formulation. We have some Fourier basis k, and here we assume any d plus 1 dimension. It's any dimension. And the pi is a momentum conjugate, and the scalar field is described by phi. This is quite familiar every elementary Hamiltonian. And after we introduce the creation operator, initiation operator, we can just like a dagger k and a k. It's a Fourier base k and its creation operator is a dagger. And the IR state is there are many ways to regularize IR state, but the symmetric one is this one. So this is equivalent to the one which describes this paper. Omega I. So alpha k, and this kind of looks like Bogor-Bokton indeed, but alpha k is precisely given by this. Lambda is a cutoff, which we introduce, and k lambda, and beta k, it's just a minus sign. Same expression, which is minus sign. So if we take a low energy limit, if we k is very small, this goes to half. Also, this part can be negligible, so that just 1, This is precisely the same definition of quantum states. But it's regulated by introducing field cutoff. And then, so we can just, here everything can be solvable. We can just have exact expression. We don't need some variation of that. Just we can write down, especially I just write the result. K is the integral. This is a cutoff function. Just simply this is gamma x equal to 1 when x is less than 1, and gamma x equal to 0 when x is rather than 1. That's very simple couple function. And so because we introduced these are both a creation data, looks like yeah, so looks like Bogoliubov in this is Bogoliubov transformation. So basically, so we started this state. This is the, and after Bogoliubov transformation, we just go back to the original standard vacuum. So this, of course, ends up with just vacuum, this zero state in the end. And yeah, maybe we can write it. For example, if we talk about the non-relativistic scale invariance, so this is a unitary transformation induced by this space-like scale transformation. So this is some factor which come from phase factor. These are dimension, and it's like Bogoliubov transformation. This is a scale, rescaled momentum. Familiar Bogoliubov transformation, coefficient change. And if we compactify, this is, I mean, non-compact description, but we can compactify so that it's k is like n over r. R is the radius, and n is the momentum. So we can confirm that Ln minus Ln tilde, some part of Virasoro algebra, is invariant. Then this transformation, this L transformation, and also k.
You can compactify by compactation of the space.
Yes, yes, space definition. Yes, yes. Like writing this in terms of this kind of modes.
Scalar field itself is not compact.
No, the scalar field is non-compact. Yeah, yes, yes. Scalar field is non-compact. Yes. And yeah, so yeah, these are, and then what do we find? Just the summary is like we find this kind of flow. du, and this is the same definition, which is this entanglement, and this is a coarse grain, and omega IR. And this is one description, but sometimes it is useful to combine these two into one operation, which we call k hat. It's an interaction. There are typical interaction picture and standard picture. This kind of interaction picture is k hat, and yeah, the same thing. So we can anyway like this way, and so this ku is given by this, and L is this one. And that precisely gives the Bogoliubov transformation from this boundary state. So, this is an example of CMA. Okay. So this is an example, explicit example. And finally, I just want to comment about this excited state and using this kind of framework. Okay, no question? So this is a solvable model, so we can also describe excited state. But I don't know, more general case, I don't know how to optimize variation. But anyway, for this case, we can talk about this. And we are talking about time evolution. This entanglement is now t dependent, depend on time, and you can so let me use this second description. They are equivalent, just interaction picture, because that's we use here. And omega IR, this is again same state, also state without any entanglement, no entanglement, same. But only non-trivial difference appears here, k hat. Also, because of that, we have a time-dependent state. So we input input is we start with Hamiltonian, CFT Hamiltonian. This sometimes may be time dependent, but let's just talk about static Hamiltonian. And also we need, of course, the information initial state, T40, initial state. And then basically we can determine k hat ut, and so this is output. K hat ut, and also Hamiltonian, which is actually CFT Hamiltonian, but depend on u. So I will explain to you. Maybe this is obtained by acting with k hat. Yeah, so like something like this. U k hat. More precise, it's integral. This is the but anyway, so this state and also time dependent state. This is obvious because we can act this operator here. But first we can construct this, then we can do the same MERA, this kind of construction. We can determine k hat and at the same time HCFT. So the idea is that here, so we have some seed. We have some time slice here. So this is time direction. And we have some time slice. This is each layer describe one MERA at some particular time. So we have time direction here. And so let's take U direction here. Then this is a U equals 0. This is a UV. So this is just this time evolution just describe phi t evolution, phi t. And here we have some IR. Everything is degenerate, just a trivial state. Everything actually 0, 0, 0, 0. This is 0, 0, 0. Everything is trivial. This kind of gives a boundary condition at this surface. So all these are just omega IR. And so we have some. First of all, there are CFT Hamiltonian, which define this. And once we fix time, we can construct this network, MERA network, which is given by k hat ut. Then we can construct this internal Hamiltonian in a consistent way, actually given by this kind of action, and so that it also induces k hat. And also this should give some other time is now translated to time and t. So this should be commutable. There are some, of course, integrability conditions which should be satisfied. So anyway, in this way, we have some continuous network, and this looks like kind of space-time tensor network. Maybe similar. And of course, if this previous conjecture is true, this network itself should describe space-time of gravity. But of course, we need to do anything to show this. But there are some nice framework anyway, which is quite general, even apply for free theory, which I don't have a problem.
One question. But if you do time evolution, then you start generating more entanglement entropy, right? Or if you have excited states, you also violate this log scaling and so on.
Yeah, that's fine. But here we are talking about strict UV limit. So this is a really strict UV limit. Even though we generate entanglement, the amount of entanglement generated finite. And there are very strict UV cutoff, which is very, very.
Yeah, but at some point, say, for instance, in 1 plus 1 dimension, instead of having a log scaling, excited states, you have something like like L. Does it mean that you have to change the range of fraction of your operator?
No. Okay, good. But here we are talking about quantum field theory, not the discretized model. Yeah. So this cutoff is in the end goes to 0 actually. So we can always assume logarithmic scale for finite time evolution. Maybe infinite time maybe changes, but at least we are talking about range which is finite. So always logarithmic rule is true. So log, I think you have this one, and there are some extensive contribution which is proportional to time maybe.
Yeah.
But we assume always this is much larger than this one because we can always take epsilon goes to 0. This is a reason. This is a high energy viewpoint. But if we discretize, I totally agree with you.
So basically, you are studying kind of small excitation.
Yeah, so small.
Interactive excitation, but some in condensed matter terminology.
Yes. Yeah, I think I think so. I think you're right. Yeah. So yeah, that's a difference here. So if we, indeed, if this term is gets smaller than this one, then we lose this asymptotical ADS condition. Space-time is different from anti-De Sitter space. And still, we expect the holography works, but there are many, unknown things for that. So we hesitate to do that. But it is possible. This term gives some volume law condition, some for internal degree free. But this gives some very UV degree free.
I'm still confused. So usually to create excited state,
yes.
add perturbation or change Hamiltonian
Yes.
quench.
Yes.
Here,
Yeah, I will explain actually quench here. So maybe, yeah. So indeed, my final example is quantum quench. But in quantum field theory sense, maybe it's different. So just quantum quench. So, but we have just massless some scalar field, but we have mass time dependent mass, so that suddenly changes at t equals 0. T equals 0, we started at m0, massive scalar, but suddenly goes to 0 mass. This is a quantum quench. And then we can write down explicitly phi 0 state, which is given by, because everything is solvable and Gaussian, so we can have this Vk in diagonal minus k. And we need the information of initial state. This is just after the quench. We are talking about this state just after the quench. It is excited because Bk is not 0. So Ak is detail is not so important. Bk square, and Bk is some quantity described by this. It's k dependent, and it's m0 k square force, and the same expression 1 minus 1. So for k equals 0, this term is very large. So this becomes very large. That means we have very large local box transformation. So yeah, also we can approximate this by boundary state, but here we just take seriously this quench and we find exact state. So this case we can talk about time evolution. So we just try to find phi t and construct MERA, and that corresponds to this simple answer is actually works for this nice example. So we just have only non-trivial factor here, time dependent factor, also u dependent factor, times the other part is the same, and this cutoff function is same as before. A dagger k, this is Bogoliubov transformation. And the non-trivial thing is just this function. And roughly speaking, this gives the strength of this entanglement. How many entanglement we put? And we can compute, but result is not that so simple. So we only have some numerical plot for this, even though we can write some very long lines of this equation for this. But the result looks like this. So we have some time. And also let's take holographic space direction. So it's like exponential. So essentially exponential minus u. U is the energy scale, length scale in this exponential length scale here. And then so we can plot this value of chi ut, and chi ut becomes 1/2 at the just m0 goes to 0. So if there are no quench, just if we start with massless field, and then chi is always constant. And so if we plot this, then it's like numerical. But we put color when chi u take this absolute by chi takes a very large value, like this range and this range and like this. Some wave-like behavior, and the wavelength is very large and goes to infinity like this. this region, I put color, is this chi gets very large. And here is the chi bumper. So only this region. And we think this is kind of approximate light cone. So if you excite the system, this is anti-Doshita space, and this is radial direction, and you quantum frequency hit UV of the anti-Doshita space, then gravitational wave propagates, and it roughly within the light cone. So of course, this is a free field example. We don't expect the Einstein gravity, and we don't expect any definite causality. But roughly, what we find is like this. So, and if we compute entanglement entropy, it's so we start with maybe expression, but we can estimate logarithmic divergence. But in addition to do that, we have some linear growth, some constant time t, always linear growth here. And at least finite time, this becomes finite, and we can take epsilon goes to 0. And this is actually, this linear growth aspect true in any dimension. So originally, this is first derived by Calabrese and Caddy for 2D, but our method also says that for free theory, this is true in any dimension. And indeed, this is confirmed by holographic calculation method.
So just to clarify, I've understood. So then you say that this linear growth, because you do a global cleanse in the CFT, this is actually what is giving you the light cone in the.
Yeah, exactly. And in a higher dimension. Yeah, so this is my end of my talk today. Thank you so much.
So z equals 0, z equals to, so you start from
This is ADS boundary here. The other one, 0. Sorry, I said u equals 0 here. Because epsilon is very, very small.
yeah.
Yes.
So that's UV.
UV, yes.
So this means that okay. So but t equals 0, you do the quench.
Yes,
And,
exactly.
this strength of this entangler
Yes.
should grow, but it propagates from UV to IR.
Yes. Exactly. Yeah, UV too.
Because even if this light cone doesn't approach IR, IR wave function is still affected because how to say?
Yeah.
IR wave function is given by this exponential operator applied to.
Yes. On Bandai kind of.
But
Here.
this size of the light cone is somehow related to this entanglement for some given section SA. Is it obvious that you have CT term from this construction?
Yeah. Anyway, we expect some saturation at size of A.
But this CT behavior is
Only true for
obvious
this
from,
region. Small time.
but still, I don't see the direct connection between this light cone and
Yeah, we can roughly connect this guy to entanglement entropy. So here, chi square and the integral over u gives the entanglement entropy. So we estimate that way.
I see now that calculation is easy to see.
Okay.
So these ripples that you see there in entanglement, that you say that, well, this is going to be the analogs of a gravitational wave and so on. What does it mean at the level of the CFT?
A CFT, it's anyway, as a propagation degree of freedom from the UV to IR.
Like that I wouldn't expect some ripples.
You're right. But anyway, at least this definition, maybe depend on some coordinate. How to choose this kind of basis and so on. Because anyway, this is one basis to specify momentum. Maybe it's possible that that's kind of artifact. If we have some sharp line, that would be really nice. But
I have another question. So we know that in tensor networks we have this gauge degree of freedom, and we can change the redefinition of the body indices and so on. What's the connection here with what happens in gravity? So is it some symmetry of the space-time or something?
And gauge symmetry.
Yeah.
Gauge symmetry is okay. We always keep everything is gauge invariant like this, but this gauge symmetry is very important to get a local physics of gravity. I remember I mentioned a little bit, but I mean here this is a quite vague description. We have some Tadashi space, but it's roughly covered like this way. It's very coarse-grained description of gravitational space-time. But if you couple gauge field and make it very strongly coupled, then we expect we get some better, finer description of the space-time. And we can, for example, the meaning of U and T gets more sharper. That's something we expect. So it's quite, I think, very, very interesting direction.
So for very small quench, like very weak quench, is it obvious that this is somehow equivalent to the boundary to bulk propagator?
Boundary to bulk to bulk. Yeah. Right.
So, but we also in ADS-CFT there's also the other way around. There's the time reverse process where you can go back to boundary.
Oh, okay. Yeah.
So is this just what does this correspond to?
We have this, and we can specify any state here. So we can start with this state and going back. So then basically time reverse allowed to do that.
Actually, I could not really follow the argument in which you obtained this operator K of U for free massless scalar.
Yes.
So
how did you obtain?
Yeah, that's also quite very good point on that. There ambiguity first of all, I should say, because we just specify this. So what we know is that we have some state at t equals 0, and we have some unitary operation, and so we have something like this, and we have some state. What we know is just this state, and we know this state. And but this is a unitary transformation, so we can take any also different unitary transformation which map this state to this state. There are one big ambiguity, but we fix this ambiguity by assuming this is Gaussian because this is a solvable theory. So we just want to find some simplest choice. So we basically say everything is proportional to this, and so this is the local. We need this is actually given by pi and pi in a local language, like this way. So it's a local expression, and we fix some basically cutoff function. Of course, ambiguity of cutoff function. Let's fix just one of them, and then only possibility is at some non-trivial function pi u here, some u-dependent function, and this can be uniquely fixed by just choosing these two states. Because this is a Bogoliubov transformation for at each wavelength. So this wavelength surface corresponds to U.
So this kind of guesswork can work only for this scalar.
Yeah, and some free system. So the interacting system are actually quite very good. That's indeed that's one problem. And holography suggests that there are one nice way to do this, and if you find it, that's probably everything. But so far, only this structure, for example, is free.
I see.
So, sorry. So the emergence of this speed of light somehow has to do with a maximum rate of how this MERA can scramble information.
Yeah, that's good. Yeah, that's interesting. I think so. Yeah, I think so. But yeah, anyway, this defines the MERA scrambling speed. But it's not that sharp line, so it's like a lot of line. So, definition is quite obvious, but should be related.
Maybe if one could make an argument that there should be a upper bound.
Right. Okay, yeah. Upper bound. Yeah, but unfortunately, this free model is not allowed to do so. But if we think of a strongly coupled case here, there are some small tail actually here. This is approximately right. Slightly value changes here. there are no sharp right cone.
But you can give an upper bound, no? With free province on bounds and things like this.
About chi.
Yeah.
That's possible, yes, yes.
Okay.
Upper bound of chi is possible. Yeah. It's not infinite.
No further questions? If not, let's thank
Thank you very
you
much.
again.
Thank you.